You know the patterns. The interview hands you a problem. Where does the method go? This is the dojo from the NBX STUDIO, and this is the method the whole series runs on. 6 steps, in order, that take you from a question you've never seen to code you can defend. Here are all 6, and the order genuinely matters. Read and draw. Spot the signals. Match the pattern. Plan in plain English. Code it clean. Test and analyze. Most candidates start at step 5 because writing code feels like progress and staring at a problem feels like failing at it. But interviewers grade steps 1 to 4 at least as hard as the code, and often harder. Read the problem 3 times, and I mean literally 3, not twice. People miss a constraint on the first pass and invent one on the second. Then draw the input and the output, physically on paper. Write the edge cases down before you forget them. Empty, single element, duplicates, negatives. Finish by saying what's being asked, in your own words. If you can't say that sentence, no amount of code will rescue you. Step 2 is what this whole series is built around. Problems announce their own pattern, and the announcement is usually a single word. Sorted. Contiguous. All combinations. Shortest.
Frequency.
Nested. Read the question again with a pen and circle the nouns and adjectives that constrain the input because those words carry the pattern. Verbs tell you what to return. Constraints tell you how to get there. From the signals, name 1 or 2 candidate patterns. Not 10 and not none. Then ask honestly whether that pattern's core idea applies here. 2 pointers works only because sorted lets you eliminate a whole side. With nothing sorted, the reasoning collapses. Say your candidate out loud. This looks like a sliding window because the question says contiguous. Wrong out loud is recoverable and invites a hint. For silent minutes is not. Interviewers can't give you credit for thinking they never heard. This is the step candidates skip, and it's the one that changes the outcome. Explain the approach in plain English before writing anything. Then walk your own example through it by hand, out loud. You'll catch half your bugs here, for free, because tracing an idea is faster than debugging code. An interviewer who heard a clear plan forgives a syntax error. Quick 1. You've read the problem, the array is sorted, and it asks for a pair. What next? Start writing the 2-pointer code. Say the pattern out loud, and walk an example. Or check whether a HashMap is faster. Have a think and pause if you'd like. Ready? Say it and walk an example because the plan is what's being graded, and it's cheap to change. Now you write it, and the goal is readable rather than clever. Use names a stranger could follow, left and right, not I and J, when left and right is what they actually mean. Start with the simple version that works. Don't optimize while you type, because premature optimization reads as uncertainty, and speeding up correct code is far easier than correcting fast code. Trace your own code with the example out loud. Find your own bug rather than letting the interviewer find it, because one of those looks considerably better. Then run the edge cases from step 1. State your time and space complexity without being asked. 10 seconds, and the difference between finished and abandoned. Say the 2 values and stop, because nobody wants a lecture at the end of an interview. Here's the table this whole series builds, and it's worth writing out by hand once. Sorted plus a pair means 2 pointers. Contiguous or subarray means sliding window. Sorted plus find means binary search. Frequency, or have I seen this, means a hash map. Nested or brackets means a stack. Shortest or fewest steps means breadth first search. All combinations means backtracking. Number of ways or minimum cost is dynamic programming. Intervals or scheduling means sort, then greedy. And cycle, or the middle, means fast and slow pointers. 10 rows. Copy them onto 1 card and read the card before every practice session. 3 things to take with you. Read before you reach, because a pattern chosen from half a problem is a wrong pattern. The signals are in the question, and circling them is a real technique. And say the plan out loud because the plan is what's actually being graded. Next up is pattern 1, 2 pointers, where 15 checks become 3. 10 patterns, 1 chapter each, and then 5 real problems solved with nothing but this method. A shelf of books, sorted by price. 15 pairs to check, or 3. So what actually changes? Pattern 1 of 10 in the NBX STUDIO dojo, 2 pointers. It's the one that turns a nested loop into a single walk, as long as the data is sorted. Before any code, Learn to read the question, because problems announce their own pattern if you know the words. When the input is already sorted, somebody put that ordering there deliberately. When you're asked for a pair, exactly two things. When those two must add to a target. And when it says palindrome, which is the same idea, wearing a different coat. But if the array is not sorted, none of this holds, and that's a HashMap problem instead. Two of those signals in one sentence, and you can stop reading. Read the question before you read the array, and half the work is already done. Here's the version everybody writes first, and there's nothing shameful about it. Pair every number with every other number and check the total. For 6 items, that's 15 pairs, fine. For 1,000 items, it's 500,000. For 1,000,000, it's 500 billion, and your interview is over before the program is. The 2-pointer version checks 3 pairs on that same 6-item list, 1,000 on the 1,000 and 1,000,000 on the 1,000,000. That gap isn't a micro-optimization, which is why interviewers keep asking it. Picture a shelf in a bookshop, already sorted by price. £1, 3, 5, 7, 9, and 11. You've got a gift card for exactly 12, and you need 2 books that total it, no change given. The obvious move is to check every pair. 1 and 3, 1 and 5, 1 and 7, and so on, all the way around. 15 combinations for 6 books. It works, and on a shelf this size, you'd never notice the cost. But hold on to that number, 15, because we're about to make it 3. Here's the smarter move, and it starts before any comparison at all. You stand at the cheap end of the shelf, and a friend stands at the expensive end. Left equals 0 puts you at the first position, holding the £1 book, so left is 0. Then right equals len of nums minus 1 puts your friend at the far end on the 11, so right is 5. That minus 1 catches people out constantly. Len of nums tells you how many books there are, which is 6, but positions start counting at 0, so the last one is 5, not 6. Nothing has been compared yet. All we've done is decide where to stand. While left is less than right just means carry on until the two of you bump into each other, because once you've met, there's nothing left that you haven't already considered. Then current equals nums of left plus nums of right, which is a formal way of saying add up the 2 books you're each holding. That's £1 plus £11, so current is 12. And the first thing we check is whether current equals target. It does, first comparison, and that wasn't luck. The shelf being sorted is what let us start at the 2 extremes, and the extremes are where the biggest and smallest totals live. Quick one, and it's from the dojo itself. We're holding £1 and £11. That totals 12, and 12 is exactly the gift card. So, what happens now? Do we keep looking for more pairs? Do we tell the friend to pick something cheaper? Are we done, and we hand back the answer? Or do we start again from the beginning? Have a think, and pause the video here if you'd like a moment longer. Ready? We're done. The question asked for a pair, we have 1, and carrying on gains nothing. Return left comma right hands back the 2 positions, 0 and 5, rather than the prices themselves, because that's what the question asked for, and it's what an interviewer expects. 1 pair out of 15. That was a friendly example though, with the answer sitting at the 2 ends. So let's make it hard, because what matters is how a pattern behaves when the guess is wrong. Same shelf, but the gift card is only £8 now. You're still holding 1, your friend is still holding 11, so current is 12, and we're £4 over. Somebody has to change book, and this is the question the entire pattern turns on. Think it through with me. If you, on the cheap end, reach for something pricier, the total can only go up, and we're already too high. So L if current is less than target is the branch we did not take this time. We fall through to else, which is the too big case, and the only person who can bring the total down is your friend. Right minus equals 1 moves your friend 1 place to the left, so they put the 11 back and pick up 9. New total. 1 plus 9 is 10. Still over budget, so nothing is solved yet. But look what that single step quietly bought us. Every pair involving the £11 book has just gone. All 5 of them. And we never looked at 1. We didn't need to. The shelf is sorted. So if 11 was too dear beside the cheapest book, it's too dear beside every book. That is the trick. The rest is bookkeeping. Your turn again, and this one separates memorizing from understanding. 1 plus 9 is 10, and the budget is still 8. So, what happens next? Do you pick a pricier book, moving the left pointer right? Does your friend go cheaper again, moving the right pointer left? Do you both move at once? Or is there simply no answer? Have a think and pause here if you want longer. Ready? Your friend goes cheaper again because the total is still too big. Same rule as last time, and it will be the same rule every time. So your friend steps down once more, putting back the 9 and picking up 7. 1 plus 7 is 8, the budget exactly, and we return the 2 positions again. Count what we actually did. 3 comparisons on a shelf where checking every pair would have been 15. And the number that matters isn't 3, it's the shape of it. Every single turn of that loop threw away a book for good, which means the work grows in step with the shelf instead of exploding. Double the books and you roughly double the checks. That is what big O of n means, and it's why this survives a million books when the obvious version doesn't. Here's the entire pattern on one card, and it costs big O of n in time and big O of 1 in space, because 2 integers is the whole of the extra memory it ever needs. Total too small? You move up because you're the only one who can add value. Total too big? Your friend moves down because they're the only one who can take it away. And if they meet without ever hitting the target, no such pair exists, and an empty list is the right answer rather than a failure. This pattern is worth real effort because it isn't one problem, it's 4. 2 sum 2 is what we just wrote. Valid palindrome compares the 2 letters and walks in. 3 sum fixes one number and 2 pointers the rest. And container with most water moves whichever wall is shorter. Do all for this week. 3 things to take with you. The signal is a sorted input and a question about a pair. The move is to start at both ends and let the total tell you which side steps. And every step throws away work you never have to do. Next in the dojo is sliding window, for when the question stops asking about a pair and starts asking about a stretch. Go and do 2 sum 2 now, while the shelf is still in your head. A row of houses, each with a number on the door. One question about them, a billion steps or 6,000. Pattern 2 of 10 in the NBX STUDIO dojo, sliding window. This is the one that turns a nested loop into a single pass by refusing to count anything twice. Same drill as last time. The question tells you the pattern if you read it properly. Watch for subarray or substring, both meaning a run of items that sit next to each other. Watch for contiguous, which is the formal way of saying the same thing, and a size or a limit, which means either a fixed K or a rule the window must keep obeying. If the items don't have to be adjacent, this is not your pattern, and you're probably looking at a HashMap or dynamic programming instead. Contiguous is the word to watch for because it is doing more work than it looks like. Here's the obvious version. Stop at every position and add up the whole window from scratch. With 6 houses and a window of 3, that's 12 additions, which is nothing. But a million houses with a window of 1,000 is a billion additions, and that program does not finish while anybody is watching. The sliding version does 12 for the small case too, and 2 million for the big one. The difference is what you refuse to redo. You're on a train, looking out of a window that shows exactly 3 houses at a time. Each house has a number painted on the door. How many cookies that house baked today? 2, 1, 5, 1, 3, 2. You want the 3 houses in a row that baked the most between them. The slow way is to stop the train at every position and count all 3 houses again from nothing. It works, and on 6 houses you'd never feel it. On a million houses with a window of 1,000 you would feel it, which is why the pattern exists. Window sum equals sum of nums up to k. That :k slice means the first 3 houses, position 0, 1, and 2, so 2 plus 1 plus 5 is 8. And max sum starts as that same 8 because 8 is the best score so far, for the very good reason that 8 is the only score so far. Max sum is 8. Hold on to this moment, because it is the only time in the whole algorithm that we add a full window from scratch. Everything after this is repair work. Now the train moves, and the loop starts at k rather than at 0, because the first k houses are already counted. 2 things happen to your view, and only 2. A new house comes in, house 3, which baked 1 cookie, so we add it. And a house leaves, house 0, which baked 2, so we subtract it. 8 plus 1 minus 2 is 7. Notice what we did not do. We never re-added houses 1 and 2. They never left the window, so their cookies were never in question. Straight from the dojo. The window total just dropped from 8 to 7. Is 7 the new best? Yes, 7 is the new record. Or no, 8 was better, and we keep 8 as the maximum. Have a think, and pause here if you'd like a moment. Ready?
No.
7 is now. 8 is the best ever seen, and the question asked for the best. That's what this line is for, and it's the line people skip. Max sum equals max of max sum and window sum. Window sum is the total you are looking at right now, and it goes up and down as the train moves. Max sum is the best total you have ever seen, and it only goes up. Two variables, two completely different jobs, and confusing them is the most common way to get this pattern wrong in an interview. Off it goes again. House 4 comes in with 3 cookies, House 1 leaves with 1. 7 plus 3 minus 1 is 9, and 9 beats our old record of 8. So max of 8 and 9 is 9, and the record moves. 2 arithmetic operations for a window of 3. And here is the part that matters. That would still be 2 operations for a window of 1,000, because the repair work has nothing to do with how big the window is. Last stop. House 5 comes in with 2, House 2 leaves with 5, so 9 plus 2 minus 5 is 6, which is not a record, so max sum stays where it is. And we return 9. Every possible window of 3 has now been checked, and the winner was houses 2, 3, and 4. 1 pass down the street, 2 operations per step, and not 1 house counted twice. One more thing, because sliding window arrives in 2 shapes and interviewers use both. The fixed window is the one we just wrote, where the size never changes and the window simply slides. The variable window is different. It grows from the right until some rule breaks, then shrinks from the left until the rule holds again. Longest substring without repeating characters is the classic. Grow until you hit a repeat, then pull the left edge past it. Same idea, same refusal to recount. Fixed size, you slide. Stated rule, you grow and shrink. For to go and do, and I do them in this order. Maximum average subarray is the fixed window you just wrote, almost line for line. Longest substring without repeating is your first variable window. Permutation in string adds a frequency count inside the window. And minimum window substring is the hard one that ties it all together. 3 things to take with you. The signal is contiguous, a run of neighbors rather than any old selection. The move is to repair the total instead of rebuilding it 1 in and 1 out. And keep 2 variables apart, the window you're in and the best you've seen. Next in the dojo is binary search, where instead of sliding a window across the data, we throw half of it away on every single step. Go and do maximum average subarray first. 1 million names and 20 guesses. So, where do the other 900,000 names go? Pattern 3 of 10 in the NBX STUDIO dojo, binary search. The one where every single step throws away half of everything that's left. Read the question first, as always. The input is sorted, which is the precondition, and without it, none of this works. You're asked to find something, a value, or a position. Or you want the first or last thing that satisfies a rule, which is the sneaky version. Or the kth smallest, which is that shape again. If log n appears in the required complexity, the interviewer has told you the answer outright. Not sorted? Then sort first, or pick a different pattern. Sorted plus find is the pair to watch, because sorted is what makes elimination safe. Scanning means checking every item until you hit the one you're after. On 10 items, that's up to 10 checks, which is nothing at all. On 1 million, it's up to 1 million, and on 1 billion, it's 1 billion. Binary search does 4 checks on 10 items, 20 on 1 million, and 30 on 1 billion. Look hard at those last 2, because going from 1 million to 1 billion 1,000 times the data costs you 10 extra guesses. That's what logarithmic means in practice. You know this game already. A friend thinks of a number between 1 and 100, and every time you guess they say higher or lower. Guessing 1, then 2, then 3 could take 100 turns. So you guess 50. Higher. Then 75. Lower. Then 62. Every guess throws away half of what is left, and that's the entire pattern. Here it is on 10 sorted numbers. 2, 16, 56, up to 91, and we're hunting for 23. Same game, same rule. Guess in the middle, and let the answer tell you which half to throw away. 2 variables mark the edges of the range we are still willing to look in. Left equals 0 puts the low edge at position 0. Right equals len of nums minus 1 puts the high edge at 9. Right now the answer could be anywhere in those 10 positions, and that's the honest state of our knowledge. Every guess from here shrinks the range. 10 possibilities become 5, then 2, then 1. Watch the range, not the values. While left is less than or equal to right, keep guessing. Hold that equal sign. We'll come back to it. Mid equals left plus right, integer divided by 2. 0 plus 9 is 9, and 9 halved rounding down is 4, because those two slashes mean divide and throw away the remainder. So we look at position 4, which holds 16. Is 16 our target? No, 23 is bigger. And because the list is sorted, everything left of 16 is smaller still, so none of it can possibly be 23. Straight from the dojo. We found 16 at the middle, and our target is 23. 16 is smaller, so where do we look now? The left half, the smaller numbers. The right half, the bigger numbers. Or start over. Have a think, and pause the video if you'd like a moment. Ready? The right half, because the list is sorted, so everything left of 16 is smaller than 16, and 16 was already too small. So left becomes mid plus 1, and that plus 1 is the first bug people write. Why not just mid, though? Because we've already checked position 4, and it wasn't our number, so including it again buys nothing, and worse, the range would stop shrinking and the loop would spin forever. Left moves to 5. And look what one guess did. Position 0 to 4 are gone, including the 16 we tested. Half the list, and we looked at one of them. New middle. 5 plus 9 is 14, halved and rounded down is 7. Position 7 holds 56, which is bigger than 23. Same reasoning as before, mirrored. Everything right of 56 is bigger than 56, and 56 was already too big, so all of that can go too. The else branch fires. Right becomes mid minus 1, and the top edge drops to 6. 2 guesses in, and 8 of the 10 are already out of the running. Stop and look at the board for a second. The range is now position 5 and position 6, and nothing else. 10 candidates down to 2 in 2 guesses. 8 numbers were never examined, never compared, never even read. They weren't examined at all, they were eliminated by an argument, and the argument was simply that the list is sorted. Mid is 5 plus 6 halved, rounding down to 5. Position 5 holds 23. That's our number, so we return the index, and the answer's 5. 3 guesses for 10 items. For a phone book with a million names, that's about 20, and for every page Google has indexed, somewhere around 33. Doubling the data costs you one more guess. Every time forever. One more, and this line causes infinite loops in real interviews. Why the equals in while left is less than or equal to right? Because a range of one item still needs checking. Because it makes the loop faster. Or because it wouldn't compile. Have a think, and pause here if you like a second. Ready? A range of one still needs checking. When left and right meet, there is one candidate left, and dropping the equals walks past it. Almost every binary search failure is one of these lines, so learn them together. Left equals mid plus 1, never mid, because mid is already checked and leaving it in stops the range shrinking. Right equals mid minus 1, for the same reason on the other side. The loop runs while left is less than or equal to right, with the equals, so a single remaining candidate still gets looked at. On very large arrays, left plus right can overflow, so left plus the half difference is safer. For lines, write them from memory. That's the whole surface. Get those right, and binary search stops being the pattern you dread, because everything else about it is the guessing game you already knew. For to go and do. Binary search itself, to get the template into your fingers. First bad version, which is binary search on a yes or no answer rather than a value. Search in rotated sorted array, which is the one interviewers actually ask. And Coco eating bananas, where you binary search the answer itself rather than an array. 3 things to take with you. Your signal is sorted plus find, and sorted is what makes elimination safe. The move is to guess the middle and throw away the half that cannot hold the answer. And the bugs live in 2 lines, mid plus 1 and mid minus 1. Next in the dojo is the HashMap, which is what you reach for when the array isn't sorted, and sorting it would cost more than the search saves. Go and do binary search first. Everyone against everyone, or one notebook and a single walk. Why is one so much faster? Pattern 4 of 10 in the NBX STUDIO dojo, HashMap. The one that buys you instant lookup, and the one people reach for without being able to say why it's fast. Here the giveaways are about memory rather than order. Frequency, or count how many times, which is a tally, and a tally wants a map. Duplicate, or have I seen this before? Anagram, which is just 2 frequency tallies compared. And 2 sum on an unsorted array, because with no sorting you cannot 2-pointer it. If the array is sorted and you need a pair, go back to pattern 1 instead. Ask yourself whether you keep needing to look something up. If you do, write it down. Pairing every person with every other person. With 4 people, that's 6 pairs, which is fine. With 1,000, it's 500,000. With 1,000,000, it's 500 billion. Walking with a notebook covers the room once for 4 people, once for 1,000, and once for 1,000,000. One pass, whatever the size, and the cost of a lookup does not grow with the number of things you have written down. That last part is the bit worth understanding. You're at a party, and everybody has a number printed on their shirt. You need to find 2 people whose numbers add up to 9. Standing in line, you have 2, 7, 11, and 15 in that order, and you can only walk the line once. You could make every person to stand next to every other person and check, which works and takes forever. Or you could carry a notebook and write down each person as you pass them. That notebook is the whole idea, which means everything else here is bookkeeping. Scene equals empty braces creates the notebook. In Python, those braces make a dictionary, which is a set of pairs, the way a phone book pairs a name with a number. Ours pairs a shirt number with the position we met them at, and right now it is empty, because we have not met anybody yet. This line starts the walk. Enumerate hands us 2 things at once. The position, I, and the number on the shirt, number. So we meet 2, then 7, then 11, then 15. One walk, one person at a time, and no going back, which is why the notebook has to exist at all. First person, shirt number 2, standing at position 0. Complement equals target minus number, so 9 minus 2 is 7. Read that as a question, not a calculation. It's you saying, I've got a 2, so to reach 9 I need a 7, and I need one I've already walked past. Is there a 7 in the notebook? Empty, so no. Nothing to match against. Nobody is behind us yet, which means there is nothing to match, exactly as you'd expect from the first person in the line. Straight from the dojo. We just wrote down that person 2 is standing at position 0. Why bother? Just for fun. Because somebody later might need a 2 to complete their pair. Or to count how many 2s there are. Have a think, and pause the video if you like a moment. Ready? Because somebody later might need a 2. Every person we write down is a favor to somebody further along the line, and that is what saves the second loop. So scene of number equals I, which reads as, I saw the number 2 at position 0. Into the notebook it goes. One line, written once, and never touched again. Why bother writing it at all, when this person did not match? Because somebody further down the line might need a 2, and we want the answer waiting rather than a second walk through the room. Now look at where that line sits, because this is the one people actually ship. The check comes first and the right comes after it, never the other way round. If we wrote the number down before asking whether we had seen it, then a 4 with a target of 8 would look in the notebook, find itself, and hand back the same position twice. A pair of one person. Order matters, which is why the check comes first. Next person, shirt number 7, at position 1. Complement is 9 minus 7, which is 2, so they need a 2. Here is the moment the whole pattern exists for. Instead of walking back down the line looking for a 2, we ask the notebook instead. There it is, a 2, met at position 0. That question took the same amount of time it would have taken with 1,000,000 entries in the book, and that's what a hash map buys you. Return scene of complement, I. Scene of complement is where we met the 2, position 0. And I is where we are now, position 1. So the answer is 0 and 1. 2 people out of 4 found on step 2, and we never looked at 11 or 15. We walked the line once forwards, and the notebook did all the remembering. That's the shape of almost every hash map problem you'll meet. One more, and interviewers do follow up with this. A hash map lookup is called constant time. What does that actually mean? That it takes 0 time. That the time does not grow as the map gets bigger. Or that it's always faster than an array. Have a think, and pause here if you want longer. Ready? The time does not grow with size. A lookup in a map holding 1,000,000 entries costs about what it costs in one holding 10. Nothing here is free, and an interviewer will ask. Time went from n squared to n, which is an enormous win. But space went from constant up to n, because in the worst case the notebook ends up holding every single person in the room. 2 pointers, by comparison, uses no extra memory at all, but it demands a sorted array. So the honest answer is that you are spending memory to buy time. Say that out loud when you propose it, because naming the trade is what makes it sound deliberate rather than lucky. For to go and do. 2 sum, which is the one we just wrote. Contains duplicate, which is the simplest have I seen this in existence. Valid anagram, which is 2 tallies compared. And group anagrams, where the key you choose is the whole puzzle. 3 things to take with you. The signal is have I seen this before, in any of its disguises. The move is to write down what you pass, so the answer is a lookup instead of a search. And the trade is memory for time, which you should name before you're asked. Next in the dojo is the stack, which is what you reach for when the order things were opened in, is the thing that matters. Go and do 2 sum first in 1 pass. Shirt, then jacket, then scarf. Now take them off. Why can't you choose the order? Pattern 5 of 10 in the NBX STUDIO dojo. Stack. Last in, first out, and the one pattern whose shape you already use every morning without noticing. Everything here is about nesting. Parentheses or brackets, which is the classic. Nested anything, tags, folders, function calls. Next greater element, which sounds unrelated and absolutely is not. Undo or back button because both are a pile of things you did. And if the order doesn't matter at all, you want a set or a map instead, not a stack. Ask whether the most recent thing is the one you've to deal with first, because that's what a pile gives you. You pull on a shirt, then a jacket, then a scarf. Coming home, the scarf comes off first, then the jacket, then the shirt. You can't get the shirt off without dealing with the jacket, and nobody had to teach you that one. The last thing on is the first thing off, and that rule is the entire data structure. Here's the string we've to check. Open brace, open square, open round, close square, close brace. Is it balanced? Read it once yourself before we start, because your eye already knows the answer. Stack equals empty brackets. That's the pile, and it starts empty. Pairs is a small dictionary mapping each closer back to the opener belongs with. A close round needs an open round. A close brace needs an open brace, and so on. 3 pairs written once, so we never reason about which closer matches which opener midloop. Then we walk the string 1 character at a time, and every character is either an opener or a closer. First character, an open brace. Is that an opener? It is. Nothing gets checked here because openers never need checking, and an opener is really just a promise that something will have to close further along. Stack, that append puts it on top. In Python, append adds to the end of a list, and because we always look at the end behaves like the top of a pile. 1 layer deep, and the promise is recorded. That's all an opener ever does in this algorithm. Next character, an open square bracket. Another opener, so up it goes. The pile now has the brace on the bottom and the square on top. Shirt, then jacket. And here's the thing the pile is quietly doing for us. It's recording the exact order we open things in, which is the only information we'll need when the closers start arriving. An open round bracket, and on the pile it goes as well. 3 layers now. Brace, square, round, bottom to top. The top of that pile is always whatever we opened most recently, which means the top is always the thing that has to close next. That sentence is the whole reason a stack fits here, so say it out loud in an interview. Now a close round bracket. Closers are where the work happens. Stack -1 means look at the top of the pile, because in Python -1 is the last item. The top is an open round bracket. Does it match? Our pairs dictionary says a close round belongs with an open round, so yes. Stack.pop takes it off. Down to 2 layers. 1 matched pair has cancelled itself out, and the scarf is off. Straight from the dojo. We see a close round bracket, and the top of the pile is an open round. What do? Put the closer on the pile as well. Take the opener off because it matches. Or decide something is wrong and return false. Have a think, and pause the video if you'd like a moment. Ready? Take it off because it matches. A matched pair cancels, and canceling is exactly what popping the pile means. A close square arrives. Top of the pile is an open square, they match, so off it comes. 1 layer left. Then a close brace. Top is the open brace, they match, and the pile is empty. Look at the shape of the whole run. We put on brace, square, round, and we took off round, square, brace. The exact reverse, and we never chose it because the pile chose for us. Return len of stack equals 0. An empty pile means every opener that went on came back off, which is precisely what balanced means. And if the pile still had something on it, that'd be an opener nobody ever closed, so the answer would be false. True. One pass through the string, and every character was looked at exactly once. 2 lines separate working code from a crash. If not stack, return false. That's a closer arriving when the pile is already empty, like a close bracket with nothing open. Without that guard, looking at the top of an empty pile throws an error. And at the end the pile must be empty. Open open close leaves an opener stranded, and the loop finishes happily without noticing. Closer with nothing open. Opener never closed. Say both out loud because an interviewer is listening for exactly those two. Getting the happy path right is the easy half of the question. For to go and do, valid parentheses, is the one we just wrote. Min stack teaches you to keep 2 piles at once. Daily temperatures is your first monotonic stack, and it's the one that unlocks a whole family. And largest rectangle in histogram is the hard one that people remember you for. 3 things to take with you. The signal is nesting anything that opens and has to close. The move is openers on, closers check the top and pop. And the bugs live in the 2 guards, a closer with nothing open, and an opener never closed. Next in the dojo is breadth first search, where instead of a pile we use a queue, and that one swap changes the answer from any path into the shortest path. Go and do valid parentheses first. A subway map. The first time you reach a station is already the fastest way there. Always. Why? Pattern 6 of 10 in the NBX STUDIO dojo. Breadth first search. It finds the shortest path, and the only reason it works is the order it visits things in. Your giveaway word is shortest, and it's almost always literally in the question. Minimum steps or fewest moves, which is the same thing wearing a different hat. Level order, when a tree has to be read row by row. Nearest or closest, which means distance again. But if the edges have different weights, plain breadth first search is wrong, and you want Dijkstra instead. And if you only need to know whether a path exists at all, depth first is cheaper. Shortest is the word. Everything else follows from it. You're standing at Station A, and you need to reach Station E in as few stops as possible. That map connects A to B, A to C as well, B to D, C to D, and finally D to E. You could hop on any train and hope, and you might get there eventually by a scenic route. Breadth first search is more disciplined, because it refuses to guess. It checks every station 1 stop away before it looks at any station 2 stops away. Standing at A, the queue is our to-visit list, and it holds 1 entry. Visit A, 0 stops out. A deek is a list that's fast at both ends. Visited is the set of stations already queued, and it starts holding A. 1 queue, 1 set. Every breadth first search has both. The queue decides the order, and the set stops you going round in circles. While the queue holds anything, keep going. Queued pop left takes the station at the front and removes it. Front, not back, and that one word is the whole difference between this and the previous pattern. We take A at 0 stops. Is A our destination? Not yet. A stack hands back the most recent station. A queue hands back the earliest, which means the nearest, and that's why the answer comes out shortest. Now the neighbors. A connects to B and to C. For each one we ask whether we've seen it before, and neither of them has been. So we mark them visited, and push them onto the back of the queue, each carrying 0 plus 1, which is 1 stop. B goes on. C goes on. The queue now holds B and C, both at distance 1. That's the first ring of the ripple, and nothing at distance 2 can be looked at until both of these have been. Straight from the dojo. B and C are both in the to-visit list. Which do we check first? C, added last. B, added first. Or whichever looks closer to E. Have a think and pause the video if you'd like a moment. Ready? B, because it was added first. First in, first out, and that ordering is the entire reason this finds a shortest path. We take B off the front, 1 stop out, and it's not our destination. B connects to D, which hasn't been seen, so we mark it and push it on the back at 2 stops. The queue is now C at 1, then D at 2. C was added before D, so C gets looked at first, even though we're standing beside D. So the queue refuses to let's run ahead, which is exactly what keeps the distances in order. Now C comes off the front, also 1 stop out, and it isn't our destination either. C connects to D as well, and here the code does something that looks like nothing. D is already in the visited set, so we skip it. Without that skip, D gets queued twice, and on a map with a loop the search never finishes. D comes off the front at 2 stops. Still not our destination. D connects to E, and E is new, so we mark it and push it on at 2 plus 1, which is 3 stops. E is now the only thing waiting. Distances have climbed in order the whole way, 0, 1, 1, 2, 3. The Q kept them sorted without a single comparison. E comes off the front 3 stops out. Every station nearer than 3 has already been taken off and dealt with, so when we ask whether E is our destination, and it is, we return the distance it carried, 3. We compared no routes at all, because the first arrival is the shortest arrival. Here's what to remember when you're tired and under pressure. Take from the front and you've breadth first search, which fans out in rings and gives you shortest. Take from the back and you've depth first search, which dives down one branch. Pop left is BFS. Pop is DFS. And BFS costs memory because a wide ring is a big Q. Same code, one word different, completely different answer, and that trade is worth naming before anybody asks you for it. For to go and do. Binary tree level order is BFS with the rings made visible. Number of islands is BFS on a grid rather than a graph. Rotting oranges is the one where the rings are literally time passing. And word ladder is the hard one, where the graph isn't given to you and you've to build it. 3 things to take with you. Your signal is shortest or minimum steps. Reach for a Q and a visited set, always both. And the reason it works is that the first arrival is the shortest arrival. Next in the dojo is depth first search and backtracking, the same code with one word changed and a completely different personality, because taking from the back turns rings into a dive. Go and do level order first. 3 toppings. 8 different pizzas. Where does the 8th pizza come from? Pattern 7 of 10 in the NBX STUDIO dojo, DFS and Backtracking. 3 lines that generate every combination there is and undo themselves on the way back. These signals are the loudest in the dojo because the question usually says them outright. All combinations. Every possible arrangement. Subsets, or the power set. Permutations, where the order matters. Generate or find all, rather than find one. But if the question asks for a count instead of the actual list, dynamic programming is usually cheaper because building a list you only wanted counted is wasted work. That word all is the tell because if they want all of them, somebody has to walk the whole tree. You're building every pizza you can from 3 toppings, pepperoni, mushroom, and olive, which the code calls 1, 2, and 3.
How many pizzas is that?
Each topping is independently on or off, so the count is 2 times 2 times 2, which is 8, and that total includes the plain pizza, with nothing on at all. People forget the empty pizza constantly, and interviewers notice. Result is the list of finished pizzas. Backtrack is the function that does the walking, and it takes where to start from and which toppings are on the pizza. Now the first line inside, it does something that looks premature. Result, append of current, colon in brackets. Photograph the pizza exactly as it stands. Photographing happens before any topping goes on, which is how the plain pizza reaches the answer, without a single line written specially for it. Here's the whole recipe, and honestly the recipe is 3 lines. Current at append puts a topping on.
Call that the choose step.
Backtrack calls itself and builds every pizza that starts this way. Call that explore. And current.pop takes the topping back off. Call that the undo. Choose explore undo. Say that out loud a few times, because every backtracking problem you'll ever meet is those 3 lines wrapped around a different rule. We put pepperoni on so the pizza is 1 and we photograph it. Notice the call is diving rather than spreading because it isn't looking at the other toppings yet at all. Backtrack calls itself from the next topping along. Mushroom goes on 2, the pizza is 1 and 2, and another photograph is taken. Backtrack goes as deep as the branch allows before considering anything else. Straight from the dojo. The pizza is pepperoni and mushroom. After we try adding olive, what happens next? We're finished. We take olive off, then mushroom, and try pepperoni with olive instead. Or we start a new pizza from scratch. Have a think, and pause the video if you like a moment. Ready? We take the toppings back off and try a different combination because that undoing is the only thing that ever reaches the other branches. Olive goes on, the pizza is 1, 2, 3, the supreme, photographed. No toppings are left to try, so the loop ends and the call returns upward. Current, pop takes olive back off, and we're at 1, 2 again. That loop has also finished, so that call returns 2, and pop takes mushroom off, leaving just pepperoni. We've climbed back up 2 levels, and now the loop at that level can carry on to the topping it never got to. Back at the pepperoni level, the loop moves on to olive, giving pepperoni and olive, a combination we could never have reached without undoing first. This is worth sitting with, because the undo isn't tidying up. Undoing is what creates the other branches. Without that single pop, the pizza just keeps growing until it holds everything, and you finish with 3 pizzas instead of 8. Everything unwinds from the top now. Everything unwinds back to the plain pizza. The loop moves on to mushroom, which gives mushroom, then mushroom and olive, and finally olive on its own. 8 photographs. Plain, pepperoni, pepperoni and mushroom. The supreme, pepperoni and olive, mushroom, mushroom and olive. Return result. Every combination, each exactly once, because the start index means we never walk backwards. One line to be careful about, and this is the bug people genuinely ship. We save current colon in brackets, not current. In Python, a list is a reference, a whiteboard, not a photograph. Saving current itself would leave every entry pointing at the same whiteboard, and since backtracking keeps wiping that whiteboard, you'd finish with 8 identical empty lists. The colon makes a copy for characters, and without them the function silently produces nonsense. Be honest about the cost, because an interviewer will push on it. 3 toppings gives 8 subsets, which is nothing. 20 gives a million. 30 gives a billion, and the program stops being usable around there. That's 2 to the n, and it isn't a flaw in your code, because that's the size of the answer itself, which is exactly why a question wanting only a count is a different pattern. For to go and do. Subsets is the one we just wrote. Permutations swaps the start index for a use set, and the difference is worth feeling. Combination sum lets you reuse a number, so the recursion goes to I rather than I plus 1. And n queens is the famous one, where the undo is undoing a whole board. 3 things to take with you. Your signal is the word all, every combination, every arrangement. Your recipe is choose, explore, undo, in that order, always. And save a copy, because saving the list itself gives you 8 pointers to the same wreckage. Next in the dojo is dynamic programming, which is what you reach for when this tree has the same branch in it over and over. Go and do subsets first, then permutations. A staircase, and you're counting the ways up. 100 million recalculations, or 40 additions. Pattern 8 of 10 in the NBX STUDIO dojo, dynamic programming. The one everybody's frightened of, which is really just refusing to solve the same thing twice. 3 phrasings cover most of it. Number of ways, which is counting rather than listing. Minimum or maximum cost, where you're optimizing. Longest or shortest something. And the real test, can the answer for n be built from answers to smaller versions of n? If the question wants the actual list rather than a count, that's backtracking from the previous pattern. And if a locally best choice is always globally right, greedy is cheaper. Counting, optimizing, and built from smaller answers. Those 3 together mean dynamic programming. You're climbing a staircase of 5 steps, and each move is either 1 step or 2. How many different ways are there to reach the top? Your first instinct is to try every possibility, and for 5 stairs that's fine. Stair 1, stair 2, stair 3, stair 4, stair 5, and the answer comes out at 8. But try that on 40 stairs and your laptop will still be thinking about it tomorrow, because the work doubles with every stair. Every dynamic programming problem needs 2 things, and finding them is genuinely the whole job. First, the base cases, the smallest problems you know without thinking. 1 stair has 1 way. 2 stairs has 2 ways, 2 singles or 1 double. Those are given, not derived. Second, the recurrence, how a bigger answer is built from smaller ones. To land on stair, n you came from n-1 or from n-2. So the ways to reach n are those 2 added, and that sentence is what you hunt for every time. Previous 2 equals 1 and previous 1 equals 2, and those are 2 sticky notes. Previous 2 remembers the stair 2 below, and previous 1 remembers the stair 1 below. Why 2 notes and not a whole table? Because the recurrence never looks back further than 2 places, so anything older can be thrown away. Most people write this with a full array first, which is fine, but noticing you need only 2 variables is what drops the space to constant. The loop starts at stair 3, because 1 and 2 are already known. Current equals previous 1 plus previous 2, so 2 plus 1 is 3 ways to reach stair 3. Then the notes slide forward. Previous 2 takes previous 1's old value, and previous 1 takes the answer we just computed. Previous 2 is 2 now, and previous 1 is 3. That slide is where people slip because the order matters. Overwrite previous 1 first, and you've destroyed the number previous 2 was about to take. Straight from the dojo. Stair 3 takes 3 ways, and stair 2 takes 2 ways. So, how many ways to reach stair 4? 4 ways, 5 ways,
6 ways,
or 3 ways. Have a think, and pause the video if you'd like a moment. Ready? 5, because 3 plus 2 is 5, and every route to stair 4 arrived from one of those 2 stairs below it. Stair 4 is 3 plus 2, which is 5 ways, and the notes slide again. Stair 5 is 5 plus 3, which is 8 ways. That's our answer. 5 stairs, and we did 5 additions. Every stair was computed exactly once, and then only read, which is the whole point of the pattern. Look at the numbers we produced. 1, 2, 3, 5, 8. That's the Fibonacci sequence, and climbing stairs is Fibonacci, wearing a hat. A surprising number of dynamic programming problems turn out to be a famous sequence in disguise, and spotting that's often faster than deriving anything. If you write out the first few answers by hand and the pattern looks familiar, trust it and check it. Here's what dynamic programming saves you from. Written as plain recursion, stair 5 asks for 4 and 3, stair 4 asks for 3 and 2, so stair 3 gets computed twice before we've properly started. Stair 10 costs about 180 calls. Stair 40 costs over 300 million, nearly all recomputing answers the program already had. The loop does 40 additions. Same recurrence either way, because the only difference is whether you write down what you worked out. When a dynamic programming question lands and your mind goes blank, do these in order. Brute force the answers for n equals 1, 2, 3, and 4 by hand. Then ask how each relates to the ones before it, because that relationship is your recurrence. Pin down the base cases. Write the loop upward from them. And only then ask whether the array can shrink to a couple of variables. Order matters because optimizing space before the recurrence is correct is how people burn 20 minutes and end up with neither. For to go and do. Climbing stairs is the one we just wrote. House robber is the same shape with a decision at each step. Coin change moves you from counting to optimizing. And longest increasing subsequence is where the recurrence stops being obvious. 3 things to take with you. The signal is counting or optimizing, built from smaller answers. You always need a recurrence and base cases, and neither one alone is enough. And the saving comes from solving each subproblem once, then only reading it. Next in the dojo is greedy, which is what you get when the locally best choice happens to be the globally right one, and no table is needed at all. Go and do climbing stairs first. For meetings, 3 blocks of time. The sort does most of the work, but which sort? Pattern 9 of 10 in the NBX STUDIO dojo. Greedy, the shortest code in the whole series, and the one you're most likely to get wrong for a reason you can't see. Intervals is the loudest one, and it usually means meetings, bookings, or ranges. Schedule or rooms or how many at once. Merge or overlap. Minimum number of something, where you want the fewest. But if a choice now can ruin a choice later, greedy is unsafe and you want dynamic programming. And if you can't prove the local choice is always right, don't reach for greedy in an interview. Intervals plus a sort is the combination. The hard part is knowing what to sort by. You're coordinating a meeting room. For bookings came in 1 to 3, 2 to 6, 8 to 10, and 15 to 18. Some of those clash. The one that runs from 2 until 6 begins while the first meeting is still going, so those 2 are really one long block of time. Your job is to collapse the diary into the smallest set of blocks that covers everything. Intervals sort, keyed on x0, sorts every booking by its start time. The lambda is Python's way of writing a throwaway function, and here it just grabs the first number out of each pair. Sorted by start. Now here's why that matters so much. Once bookings are in start order, anything that overlaps the current block must be the very next one along. Sorting turns a question about every possible pair into a question about neighbors, and that's the whole reason this runs in one pass. Then merge starts holding just the first booking. Next booking is 2 to 6. Does its start come before the current block ends? 2 is less than or equal to 3, so yes, they overlap. So we stretch the block's end to whichever end is later, which is 6. 1 to 3 and 2 to 6 have become 1 to 6. One block now covers both meetings, and notice we never created anything new, we only widened what was already there. Straight from the dojo. 1 to 3 and 2 to 6 overlapped, because B started before A finished. So what about the block 1 to 6 and the booking 8 to 10? They overlap. Or they do not overlap because 8 starts after 6 ends. Have a think and pause the video if you like a moment. Ready? They don't overlap. 8 comes after 6, so there's a genuine gap between them, and a gap means a new block rather than a wider one. Next is 8 to 10. Does 8 come before 6? It doesn't, so there's a gap. The else branch runs, and we append it as a separate block. 2 blocks now. That's the entire decision the algorithm ever makes. Overlap means widen, gap means append. One comparison per booking, and it never revisits a decision it has already taken. That refusal to look back is exactly what the word greedy means. Last booking, 15 to 18. 15 is well past 10, so another gap and it becomes a third block. Return merged, and the diary is 3 blocks instead of 4 bookings. The whole thing cost 1 sort plus 1 walk, which is n log n for the sort and n for the walk. The sort dominates, so the honest complexity, to quote, is n log n. Now change the question and keep everything else. 3 bookings this time. 1 to 10, 2 to 3, and 4 to 5. You can only be in one room at a time, and you want to attend as many meetings as you possibly can. Not merge them, not count the blocks. Attend the most. Same function shape as before, and watch what happens if you reach for the sort you already know. Sorted by start time. The earliest booking is 1 to 10, so greedy takes it and counts it. It began first, and taking it felt obviously right. But it runs all the way until 10, so 2 to 3 is gone and 4 to 5 is gone with it. We return and 1 meeting attended. And the painful part is that you could have attended 2. The code ran, it returned a number, and the number is simply wrong. Nothing crashed to tell you. So here is the question the whole pattern turns on. Sorting by start time just cost us a meeting. What should we sort by instead? To attend as many as possible. By how long each meeting lasts, shortest first. Or by end time, earliest finisher first. Have a think, and pause the video if you would like a moment. Ready?
Sort by end time.
Shortest first sounds clever, and it also fails, because a short meeting sat awkwardly in the middle can still block 2 others. What actually matters is who frees the room soonest. 1 character changes. x1 instead of x0, so we sort on the end time. Now the earliest finisher is 2 to 3, and we take it. Start is at least last end, so count goes to 1, and last end becomes 3. Next is 4 to 5. 4 is not before 3, so it fits, and count goes to 2. 1 to 10 finishes last of all, so it is considered last, and by then the room is busy. 2 meetings attended instead of 1, from changing a single character. It is worth knowing why that works because an interviewer will ask. Whenever you take the meeting that finishes earliest, you leave the largest possible amount of time free for everything that comes after it. Any other first choice ends at the same time or later, so it can never leave you more room. Which means swapping in the earliest finisher never makes your answer worse, and that is the exchange argument, said in plain English. Say that sentence out loud in an interview, and you have proved your greedy choice is safe. Here's the part that actually separates people, and it isn't the loop. Merging intervals? Sort by start time, because you want neighbors to be adjacent. Picking the most non-overlapping meetings? Sort by end time, because finishing early leaves the most room for everything after it. Minimum rooms needed? Sort the starts and ends separately, and sweep through them. Same loop shape every time, and the sort key is what changes. Get the key wrong and the code still runs, still returns something, and is quietly incorrect. That's the failure mode to be afraid of here. Greedy is the easiest pattern to write and the easiest to be wrong about, so hold on to one test. Greedy is safe when a locally best choice can never block a better global outcome. Merging intervals passes that test because widening a block never costs you anything later. Coin change with arbitrary coin values fails it because grabbing the biggest coin first can strand you, which is precisely why that one is dynamic programming. So if you can't argue why the local choice is always safe, say so out loud and reach for DP instead. For to go and do. Merge intervals is the one we just wrote. Insert interval is the same idea with one booking arriving late. Non-overlapping intervals is where you must sort by end time instead. And meeting rooms too is the sweep and the one that gets asked most. 3 things to take with you. The signal is intervals or scheduling. The move is sort first, then one pass with a single comparison. And the danger is the sort key because the wrong one still runs and quietly lies to you. Last pattern next. Fast and slow pointers, where 2 runners at different speeds tell you something no single pass ever could. Go and do merge intervals first. 2 runners on a track. If there's a loop, they must collide. But why must? Pattern 10 of 10 in the NBX STUDIO dojo. Fast and slow pointers. 2 runners at different speeds, and the last pattern in the set. Cycle, or loop, is the obvious one. Linked list almost any question about one. Find the middle in a single pass. Circular, or does it repeat? And a constraint you'll see written explicitly. Order 1 space. No extra memory allowed. If extra memory is fine, a visited set is simpler, and you should say so. That memory constraint is usually the real signal because it's the interviewer quietly ruling out the easy answer. Picture a running track where you can't see the whole shape. For nodes, 1, 2, 3, 4, and 4 quietly points back to 2, so the last stretch is a loop rather than a finish line. 2 runners set off from the same place. The tortoise takes 1 step at a time. The hare takes 2. If the track ends, the hare falls off the end first, and we know there's no loop. If it doesn't end, something else happens, and that something is the whole pattern. Slow equals fast equals head puts both runners on node 1. Python lets you assign 2 names at once like that, and both now point at the same first node. No extra memory has been allocated at all. Not a set, not a list, just 2 references, which is the entire reason this pattern exists. While fast exists and fast.next exists, keep running. That double check is the guard. If either is missing, we've reached the end of the track, so there was no loop. Slow moves to node 2. Fast moves twice to node 3. The gap between them is 1 node now, where a moment ago it was 0. Slow moves to node 3. Fast moves 2 again. Node 3 to node 4, and then 4 points back to 2, so the hare lands on node 2. It has been round the bend, and it's now sitting behind the tortoise. The gap is 2. On a track with no loop, the hare would have fallen off by now, and instead it's lapping. Straight from the dojo, and this is the good one. The hare is inside the cycle, behind the tortoise. Will they ever land on the same node? No, the hare is simply too fast. Yes, because the hare gains 1 position per round, so they must meet. Or only if the loop happens to be an even length. Have a think and pause the video if you like a moment. Ready? Yes, and it isn't luck. Each round the hare moves 2 and the tortoise moves 1, so the distance between them closes by exactly 1, every single round. This is worth being able to say out loud because interviewers ask for it. Once both runners are inside the loop, think about the distance from the hare to the tortoise, measured forwards around the loop. Each round the hare covers 2 and the tortoise covers 1, so that distance shrinks by exactly 1 every round. A quantity that decreases by 1 and can't go below 0 has to reach 0. When it does, both runners are on the same node. It can never jump past, because closing by 1 at a time cannot skip a value. Slow steps to node 4. Fast goes 2. Node 2 to node 3, then 3 to 4, so it lands on node 4 as well. Slow equals fast, so we return true. There's a cycle. 1 pass, no extra memory, and no list of visited nodes anywhere. Now take the loop away and run exactly the same race. 5 nodes in a straight line. 1, 2, 3, 4, 5, and a proper ending this time. The question changes completely. Find the middle node in a single pass, without counting the list first, and without storing it anywhere. Look at the code, and notice what is different. Almost nothing is. Both start on node 1. Tortoise to node 2, hare to node 3. Round again. Tortoise to node 3, and the hare to node 5. Fast next is now empty, so the loop stops, and the tortoise is standing on node 3. That is the middle of 5. And it falls out for free. The hare covered twice the ground in the same number of rounds, so wherever the hare finishes, the tortoise is exactly halfway there. You never counted anything. One more from the dojo, and this one catches people out. That list had 5 nodes, an odd number, so the middle was obvious. Run the very same loop on a list of 6. Where does the tortoise stop? On node 3, the first of the 2 middles. Or on node 4, the second one. Have a think, and pause the video if you would like a moment. Ready? Node 4, the second middle. With an even length, the hair runs off the end 1 round later than you expect, and the tortoise takes 1 more step with it. If a problem wants the first middle instead, you start the hair 1 node ahead. Last one, and it is the question interviewers actually ask. You know there is a loop. Now find the node where it starts. Here is a track where 1 and 2 are the straight part, and 3, 4, and 5 are the loop, so node 3 is the entrance we are looking for. Run the usual race until they meet. Then do something that looks like nonsense. Send the tortoise back to the start. Now walk them both at 1 step each, the hair included. The tortoise leaves node 1, and the hair moves 1 along inside the loop. Step again, and they land together on node 3, which is exactly the entrance. Return slow. The loop starts at node 3. The reason is a short piece of arithmetic. The distance from the head to the entrance turns out to equal the distance from the meeting point back round to the entrance. Equal distances equal speeds, so they arrive at the same moment. You do not need to derive that in the room, but you should be able to say that sentence. Step back and look at what one loop just did for you. With a cycle, they collide, and that tells you the loop exists. With no cycle, the hair runs out of track and the tortoise is left on the middle. Restart the tortoise at the head after they meet, walk both at 1 speed, and they land on the entrance to the loop. And if you start the hair k nodes ahead instead of together, the gap stays k forever, which hands you the kth node from the end. For different interview questions, the same 2 pointers and the same 8 lines. For to go and do, linked list cycle is the one we just wrote. Middle of the linked list is the same loop with a different ending. Linked list cycle 2 asks where the loop begins. And happy number is the same algorithm on numbers instead of nodes, which is the one that proves you actually understood it. 3 things to take with you. The signal is a cycle, a middle, or a demand for constant space. The move is 2 pointers at different speeds from the same start. And the reason it works is that the gap closes by 1 per round, so a meeting is forced. That's all 10 patterns. Next comes the part that actually matters in an interview, taking an unseen problem and deciding which of these to reach for. Go and do linked list cycle first. 5 problems you've never seen. 10 patterns you have. Which one, and how fast can you tell? 10 patterns are behind us here in the NBX STUDIO dojo. Now 5 real interview problems, and the only thing that matters is how we choose. Same routine for every one of these. Read the statement. Circle the signal words. Name the pattern those words point at. Then check the core idea really applies, rather than just sounding right. And only then write anything. Watch how short step 3 gets 1 step 2 is done properly. That's the whole promise of learning patterns rather than memorizing solutions. An array of heights, each one a vertical line. Find the 2 lines that hold the most water between them. Circle the words.
2.
Maximum. A pair of elements.
An array.
2, and pair together point straight at 2 pointers. But there's a catch worth noticing. This array isn't sorted, and sorted was our signal last time. So, does the pattern still hold? It does hold, and the reasoning is worth having. Start at the widest possible container. 1 line at each end. The area is the shorter of the 2 heights, multiplied by the distance between them, because water spills over the lower side. Now move the shorter line inward. Moving the taller one can never help, since the shorter side is what caps the volume and the width only shrinks. Order of n, constant space, and no sorting needed, because the elimination argument here is about height rather than order. Find the length of the longest substring with no repeating characters.
Circle them.
Longest. Substring, not subsequence, and that distinction is the whole question. Without repeating, which is a rule the answer has to keep obeying. Substring means contiguous, and contiguous plus a rule is a sliding window, the variable kind that grows and shrinks rather than the fixed kind that slides. A set holds the characters currently inside the window. The right edge moves forward, adding a character each time and growing the window. The window never restarts, which is the whole trick, and when a duplicate turns up, the left edge moves in, dropping characters until the duplicate is gone, and the rule holds again. Every character is added once and removed at most once, so it's order of n even though both pointers move. Neither pointer ever walks backwards, and that is the property to say out loud. A sorted array was rotated at some pivot. Find a target and do it in log n time. Sorted, rotated,
search,
and order log n, stated outright in the constraints. That last one isn't a hint, it's an instruction. Log n on an array means binary search and essentially nothing else. The interesting part is that rotation appears to break the precondition, so let's look at whether it really does. Here's the insight it turns on. Cut a rotated array anywhere, and 1/2 is always still fully sorted. It can't be otherwise, because a single rotation puts one breakpoint in, and a breakpoint can only sit in 1/2. So compare mid with left to work out which half is the clean one. If the target sits inside that sorted half, search there, otherwise search the other. Still log n because we're still throwing away half the array every step. Rotation looked like it broke the precondition, and it never did. Your turn, and this is a real interview moment. A question says, find the minimum number of coins to make an amount.
Which pattern?
Greedy, take the biggest coin each time. Dynamic programming. Or backtracking, try everything. Have a think, and pause the video if you like a moment. Ready? Dynamic programming, and the reason is that greedy genuinely fails on this one. We'll see exactly how in a minute. A grid of ones and zeros. Land and water. Count the islands. Circle them.
Grid.
Connected or adjacent. Count the components. No shortest anywhere, which is interesting because breadth first search is still the natural tool here. We're using it to flood a region rather than to measure a distance. Depth first would work just as well, and saying that out loud is worth marks. Walk the grid cell by cell. When you hit a piece of land nobody has visited, that's a new island, so add one to the count. The ring spreads until the island runs out. Then flood it. Breadth first search out from that cell, marking every connected piece of land as visited so nothing is counted twice. And the outer scan carries on from where it left off. Every cell is visited once, so the cost is rows times columns. Coins of different values and a total to reach. Return the fewest coins, or -1 if it can't be done.
Circle them.
Fewest or minimum. Number of choices at every step, since any coin can be next. And subproblems that overlap, because the best way to make 7 turns up inside the best way to make 8. Minimum choices and overlap together mean dynamic programming. Those 3 together are the tell, every single time. A table where entry I holds the fewest coins needed to make amount I. Base case. 0 coins make 0. Amount 1, amount 2, amount 3. Each solved once, and then only read. And for every amount upward we try each coin and keep the best. 1 coin, plus whatever it costs to make the remainder. Amount times coins, which is a loop inside a loop and nothing worse. Here's why greedy is wrong, and it's worth memorizing because it comes up. The coins of 1, 5, and 11, and you need 15. Greedy takes the biggest first, 11 then 4 ones. 5 coins. The real answer is 3, 5, 5 and 5. Greedy failed because taking 11 stranded it, and greedy never reconsiders. Dynamic programming tries every coin at every amount, which is exactly the reconsidering greedy refuses to do. Here's what to actually do tomorrow. Do the 4 problems listed under each pattern, in the order given. Before you write anything, say the pattern out loud, and why. When you're stuck for more than 15 minutes, read the solution, then close it and write it from memory. And redo the ones you got wrong a week later, because recognition fades fast. 3 things from the whole series. The words in the question carry the pattern, and reading properly beats coding quickly. 10 patterns cover most of what gets asked, which is a much smaller job than it looks from the outside. And saying your reasoning out loud is the thing being graded. That's the dojo. 10 patterns, 1 method, and 5 problems that used nothing else. The interactive version is linked below if you want to step through these yourself. Good luck.